Okay, hi everybody. So we're going to do a brief lesson on vector calculus. Just to let you guys know, vectors are covered more extensively in multivariable calculus. So you're going to learn, about dot products and cross products and, two-dimensional vectors and three-dimensional vectors in that class. What we're going to do in this class, like our understanding of vectors is very basic. All we are going to need to do with vectors, and we'll talk about this, as we move through this lesson, is be able to represent a set of parametric equations in vector form, and be able to take a particle that moves along a curve and be able to express its motion in terms of a velocity vector. So if you think about let me draw this real quick. So if you think about a particle that moves along a curve, if you have a curve that looks like so, if you have a particle that moves along that curve, at various instances of time, there is going to be a horizontal component for velocity and a vertical component for velocity. And we're going to be able to express the horizontal components and vertical components for both velocity and acceleration in vector form. So if you have a particle at this dot here that I've marked in blue, as long as that particle is moving in this direction here, we can say that the particle is moving forward. So the horizontal component for velocity would be positive, and it looks like the particle is moving down as well. So the vertical component for velocity is negative, but there is both a horizontal and vertical component for velocity and for acceleration, and we're going to be able to represent motion using vectors in that way. Okay, so let's talk a little bit about, just really briefly, about vectors and some things that we can do with vectors, and then we'll get into the stuff that we need to know in regards to calculus. So we say that vectors have a magnitude and a direction. So magnitude refers to a length, and direction, it's clear what that means. So when we go through this lesson, we will denote two-dimensional spaces as R2 and three-dimensional spaces as R3. So when we have two-dimensional spaces, there are going to be two components that make up your vector, and then for three-dimensional spaces, there are three components that make up your vector. Okay, so for spaces in R2, which are two-dimensional spaces, vector v, so there are two ways that you will see a vector expressed. It'll be the letter for whatever the vector is, which in this case is v, and it sort of has a half. If you guys remember back in geometry, what a ray looks like, it has a half ray on top of that letter. Or you'll see vectors expressed with whatever letter you use for the vector bolded. Okay, so you will either see that with a bolded V or the notation that I use. And then vectors themselves have triangular brackets. So this vector V contains the first component a sub 1, and then the second component of that vector is a sub 2. Okay, so that is, I would say, the most common way to see vectors represented. Okay, we can also represent that vector v that we have up above using what are called standard basis vectors, which standard basis vectors are vectors of length 1 that in two-dimensional spaces will extend horizontally and vertically. Okay, so we can represent that vector v using standard basis vectors, where I can write vector v as a sub 1 times vector I. So when you look at that first vector, a sub 1, that is what is called, with vectors, it's what's called a scalar. Okay, so that's something that you multiply a vector by. A sub 2 is also a scalar. And then we are going to let vector I be the vector represented by first component 1 and second component 0, and vector j be the vector represented by first component 0 and second component 1. And we'll talk about how you add or subtract terms of a vector. But basically what you're going to do is you're going to multiply a sub 1 times this vector I, which would, when you multiply a scalar times a vector, you're going to multiply that number out front times each of the components. So that's going to transform that vector into a vector with first component a sub 1, second component 0. And then when you multiply a sub 2 times vector j, you're going to multiply that scalar across both of the components, which would make that second vector have first component 0 and second component a sub 2, and then you would just add those two vectors together, which would give you the vector with first component a sub 1 and second component a sub 2. Okay, similarly, for spaces in 3 dimensions, your vector is going to have 3 components. So there's like a horizontal component, a vertical component, and like a depth component. Okay, so the 3 components for vector v in 3-dimensional spaces would have first component a sub 1, second component a sub 2, and third component a sub 3. And we could represent that using the standard basis vectors as well. Okay, so that would be a sub 1 times vector I, where vector I would have first component 1 and then the next 2 components 0. Vector j would have first component 0, the middle component 1, and then the last component 0. And then vector k would be the vector that has the first 2 components 0, and then the third component 1. So if you took each of those vectors, multiplied the scalar by each one, and added them together, then that would give you this vector over here. Okay, so a term that you hear used quite frequently with vectors is the norm of a vector. Okay, so when you see the norm of a vector, that is synonymous with the magnitude or length of the vector. So the norm of the vector, the magnitude of the vector, the length of the vector all mean the same thing. Okay, so if we have a 2-dimensional vector, vector v, with first component a sub 1 and second component a sub 2, then its magnitude, so you will see magnitude represented 2 ways. Okay, some books will use just a set of vertical bars with the vector inside to denote magnitude. Other books will use a set of 2 vertical bars with the vector inside. So when I do this, I use the notation on the right with the 2 sets of vertical bars. Okay, so the magnitude or length or norm of a vector is calculated by taking the square root of the first component squared plus the square root of the square root of the first component squared plus the second component squared. Okay, so you can think of it, I mean, if you parallel it to something that you've learned in the past, it's kind of similar in some ways to the Pythagorean theorem. Okay, so as I mentioned earlier, we can add or subtract vectors by adding or subtracting their components. So if we have vector v sub 1 with first component a sub 1 and second component b sub 1, and vector v sub 2 with first component a sub 2 and second component b sub 2, then we can add or subtract the 2 vectors by adding or subtracting their respective components. So if I want to add vector v1 plus v sub 2, I'm going to take the 2 first components and add them together. So the first component will be a sub 1 plus a sub 2, and then I'm going to take the 2 second components and add them together. So the second component would be b sub 1 plus b sub 2, and we can do the same thing when subtracting 2 vectors as well. Okay, next thing we're going to talk about really briefly is the unit vector. So a unit vector is defined as a vector whose length is 1. And something that we can actually compute is if we are given vector v has first component a sub 1 and second component a sub 2, then its unit vector in the same direction okay, which we're going to represent with the vector u. You can find that by taking vector v and dividing it by its magnitude. Okay, so once you compute the magnitude, you can take vector excuse me, vector v and divide by the magnitude, or you can take the reciprocal of the magnitude and then distribute it across each component in the vector. So just to do a quick example illustrating that, let's say the directions ask us to find the unit vector in the direction of vector v with first component 2 and second component -1. Now, we can take that vector and represent it in component form, which we have on the left. We can also express that vector using the standard basis vectors, where we can write that vector as 2 times vector I, which again, vector I has first component 1 and second component 0, minus vector j, which vector j has first component 0 and second component 1. Okay, so if we want to calculate that, the unit vector, okay, so that's going to be vector u, sorry, and that's going to be equal to vector v, okay, which is the vector with first component 2 and second component -1. And then we're going to divide that by the magnitude of that vector. So if we want to compute the magnitude, it's going to be the square root of the first component squared plus the second component squared. So this is like the vector with components 2 and -1 divided by the square root of 5. And then all I'm going to do is I'm going to distribute 1 over rad 5 across both of those terms. Okay, so that's in component form going to give me the first component, which is 2 over rad 5, and the second component is -1 over rad 5. Okay, so that's one way of expressing the vector. We can also write that using the standard basis vectors. So this would be 2 over rad 5 times vector I minus 1 over rad 5 times vector j. Okay, so either of those two representations would be fine for that vector in particular. Okay, so I'm changing colors here because this is the stuff that you need to know as far as this class is concerned. Okay, so you guys need to be aware that we can write parametric equations in vector form. Okay, so you guys know with parametric equations, like you're going to have x equal to some function f of t and y equal to some function g of t, where both x and y are written in terms of the variable t. Again, t is the parameter of that set of parametric equations. So if we let r of t be equal to the vector with first component f of t and second component g of t, okay, if that's going to represent the position of a particle at any time t, what we're able to calculate then is the velocity vector, which is going to give us like the horizontal component of velocity and the vertical component of velocity. So we know going from position to velocity, we take the derivative of our function. So if we want to find the velocity vector, the horizontal component of that velocity vector is the derivative of f with respect to t. Okay, so that's f prime of t. And the vertical component of velocity is the derivative of the second component, g, with respect to t. Okay, so again, like we mentioned earlier, like if a particle is moving along a curve, there is going to be a horizontal and a vertical component for velocity. Okay. Similarly, there's going to be a horizontal and vertical component for acceleration as well. Okay, so the acceleration vector, we know acceleration is the derivative of velocity. So To get the acceleration vector, we are going to take the derivative of each component of the velocity vector. Okay, so the horizontal component of acceleration is f double prime of t, and the vertical component of acceleration is g double prime of t. Okay, another common thing that you're asked to calculate is speed of a particle at a certain time. And if you want to calculate speed, speed is just the norm or the magnitude of the velocity vector. Okay, so you're going to your velocity vector. If we want to get the norm of that, that's going to be the square root of the first component, f prime of t squared, plus the second component, g prime of t. And we're going to square that as well. And then lastly, total distance traveled. Total distance traveled, we said again, was like our arc length formula for parametrically defined curves. Okay, so that was like the integral from a to b of the square root of dx dt squared plus dy dt squared, which we're integrating with respect to t. Another way for you to think of that, total distance traveled is just the integral of speed on the closed interval from a to b. Okay, and those are going to be the common things that you're going to be asked to calculate for a particle in motion on a parametrically defined curve. Okay, so we're going to do an example illustrating this, and then we're going to do one free response question as well. So directions for this first example say that a particle moves in an elliptical path so that its position at any time t, which is greater than or equal to 0, is given by the following vector. Okay, so we have the vector s of t, which has first component 4 times the sine of t, and second component 2 times the cosine of t. Now, we can take this position, which is written in terms of a vector, we can also write this like as a set of parametric equations where where x is going to be equal to 4 times the sine of t, y is going to be equal to 2 times the cosine of t. So that set of parametric equations and that vector that we have drawn, those both represent the same thing. They represent the position of a particle at any time t. Okay, so if we want to find the velocity vector, okay, so that's our vector v of t. What we're going to do is take the derivative of each component. Okay, so the horizontal component of velocity is going to be the derivative of 4 sine of t, which is 4 times the cosine of t. And then the vertical component for velocity is the derivative of the second component of the position function, which is -2 times the sine of t. And then we're going to evaluate that velocity vector at time t is equal to pi over 4. So when we plug in pi over 4, cosine of pi over 4 is rad 2 over 2. So 4 times rad 2 over 2 is 2 rad 2. And then when we plug pi over 4 into the second component, the sine of pi over 4 is also rad 2 over 2. So -2 times rad 2 over 2 is negative rad 2. Okay, so that right there is your velocity vector at that time. And that tells you like in what direction your particle is moving at that particular instance of time t. Okay, so if velocity is positive, the particle is moving, if the first component is positive, that means the particle is moving to the right. If the second component is negative, that means that the particle is moving down. So that particle is moving down and to the right. Okay, second thing we're asked to calculate in part B is the speed of the particle at time t is equal to pi over 4. Okay, so if we want to calculate speed, that is the norm of the velocity vector. Okay, so that's going to be equal to the first component of velocity at t is equal to pi over 4, which we calculated that to be 2 rad 2. We're squaring that, plus the second component which is negative rad 2, which we're squaring that, and then we're taking the square root of the entire thing. Excuse me. So that's going to be equal to 2 rad 2 squared is 8, negative rad 2 squared is 2, and that becomes rad 10. Okay, so that is the speed of your particle at that particular time. Okay, so for this free response question, I want you guys, if you can, to work through this piece by piece. So pause the video as I work this through. You work it through first, and then you can check your answer against what I'm going to do. Okay, so directions here say an object is moving along a curve. And by the way, this is a calculator question. So an object is moving along a curve in the XY plane, and it has the position x of t comma y of t at time t greater than or equal to 0 with dx dt equal to 3 plus the cosine of t squared. And then we're told the derivative dy dt is not explicitly given. And then lastly, at time t is equal to 2, the particle is at position 1 comma 8. Okay, so there are 4 parts to this question. First part, part A, excuse me, asks us to find the x-coordinate of the position of the object at time t is equal to 4. Okay, so if we're trying to find the x-coordinate of position, we do have an initial condition that pertains to that. We know that at time 2, the x-coordinate of position is 1. Okay, so that's our initial condition, where x of 2 is equal to 1. And then we're being asked to calculate x of 4. Okay, so this is a net change theorem problem. So if we want to calculate x of 4, that's going to be equal to the initial position x of 2 plus the integral from 2 to 4 of, if we want to calculate x, we need to integrate dx dt, okay, which is 3 plus the cosine of t squared, which we are integrating with respect to t. So again, you want to evaluate this on your calculator. I got that to be approximately 7.133, rounded to 3 decimal places. Okay, on to part B. So for part B, question says at time t is equal to 2, the value of dy dt is negative 7. And the question asks, what is the equation for the line tangent to the curve at the point x of 2 comma y of 2? Okay, so again, if we want to find the tangent line equation, the 2 pieces of information that we need are the slope of the tangent line and the point of tangency. Okay, so the point of tangency I think is easy to calculate. We're told at time t is equal to 2. The position is at 1 comma 8. So we know x of 2 is 1. Y of 2 is going to be equal to 8. So that is our point of tangency. What we need to figure out is what the slope of the tangent line is going to be. Okay, so we know that for parametrically defined curves, dy dx is going to be equal to dy dt divided by dx dt. We're not directly told what the derivative dy dt is, but we know at time t is equal to 2. In the problem, we're told that dy dt is negative 7. And then I can plug 2 into the derivative of x with respect to t. So when I plug 2 in the place of t there, that's going to give me 3 plus the cosine of 4. So that right there, I mean, if you want to find the decimal approximation for that, that's fine. If you want to leave that answer in exact form, that's fine as well. So that's going to give us the slope. So if you do the decimal approximation, I think I found that to be approximately negative 2.983. But I'm going to leave the answer in exact form. So that's, if I want to find the equation of the tangent line using the point slope formula, it's y minus the y coordinate 8 is equal to the slope, which that's the derivative's value, which I'm going to leave as an exact answer, which is negative 7 over 3 plus the cosine of 4 times x minus the x coordinate 1. If you want to substitute that decimal approximation in, so if you want to plug this in here, that's acceptable as well. Okay, either of those is fine. Okay, on to part C. So for part C, we want to find the speed of the object at time t is equal to 2. So again, speed is the norm of the velocity vector at time t is equal to 2. So that's going to be equal to the square root of x prime of 2 squared plus y prime of 2 squared. So again, like we already determined what x prime of 2 was. It was this value here. Or if you want to do like the decimal approximation, that's fine. We know y prime of 2, based on what we had in the previous part, was negative 7. So when you plug those two values into that formula for magnitude, I got that to be approximately 7.383. And then for part D, so part D says for t greater than or equal to 3, the line tangent to the curve at x of t comma y of t has a slope of 2t plus 1. And then we're asked to find the acceleration vector of the particle at time t is equal to 4. Okay, so for this one here, if I want to find the acceleration vector, the first thing I want to do is I want to determine what dx dt and what dy dt is. So we know that dx dt, we are told that from the initial directions that were given, it's 3 plus the cosine of t squared. So if I want to find the acceleration vector, that is the horizontal component of the velocity vector. To find the horizontal component of the acceleration vector, I want to take the derivative of that function. Now, can you take the derivative of this by hand? Absolutely. But I don't want to do that here because I can take a derivative more quickly on my calculator. So if we input that function, you can, on your calculator, calculate the numerical derivative and then evaluate that at time t is equal to 4. So you should have got like x double prime of 4 on your calculator to be approximately 2.303. So if we're trying to find the acceleration vector at 4, the first component of that acceleration vector is 2.303. That is the horizontal component of acceleration. Now, the problem for us is we don't know, like we're not explicitly told what dy dt is. Okay, but we actually have enough information to figure out what dy dt is going to be because we know that the slope is 2t plus 1. Okay, so that means that dy over dx is dy dt over dx dt. Well, we know that the slope dy dx is 2t plus 1. We don't know what dy dt is. We do know what dx dt is. So dx dt we said was 3 plus the cosine of t squared. And then I can determine what dy dt is So isolating dy dt, we can do that multiplying both sides by the denominator. So it's 2t plus 1 times 3 plus the cosine of t squared. And then once you know what dy dt is, we know to get the vertical component of acceleration, we have to take the derivative of dy dt. So that's going to be like y double prime. So we want to evaluate that derivative on our calculator at t is equal to 4. And when you do that, I got the second component, or the vertical component for acceleration, to be 24.814. Okay, so those are the two components there for your acceleration vector at time t is equal to 4. And that's what you're going to need to know in regards to vectors. Hey, I know that with vectors, I can represent the horizontal and vertical components of velocity, the horizontal and vertical components of acceleration. We can like locate position. But the main thing is being able to take like a set of parametric equations and represent them using vectors. Okay, so that's definitely stuff that you need to know in regards to vectors. All right, guys, so that's it for today. Hope you guys have a great rest of your day.